I have a little bit at the end here on the central limit theorem. So I put a link to Khan Academy. Central limit theorem isn't something that you need to master, except it is really key for those inferential statistics. Remember that one of our major tools with statistics is the ability to compare the data that we have with some expected or other well-defined pattern. Problem is, if you haven't actually researched something already, you don't know what a variable's distribution of possible scores is likely to be. And many of those sources of data don't distribute normally. Now, luckily, what we found is that when you take a mean of a sample, so I take many, many different samples, those means will distribute in a normal distribution. They will actually take the form of a normal curve. This goes back to our conceptual thinking about the normal curve. That is that things in nature, in this case samples of means, but things that occur naturally, tend to be affected by a lot of different random impacts, some of which are rarer than others. So if they're very rare, they're going to be those things at the tails, and the things that are most common result, and this is the average that occurs on any type of distribution, is going to be the most common result. It's going to stack up in the middle and give us that hump that we're used to seeing in the distribution. I just pulled this from our Unit 4 data set. This is a 2% out of whatever it is, 1,900 or so school mean scores. You can see at 2% we've got a lot of variation. This is just 6 different random samples. But the mean is kind of similar, the standard deviation kind of similar. As I move forward to larger and larger n sizes though, 20% starts to fill it in more, 60% even more, 80%, 100%. So here we're seeing the school means just gradually fill in, gradually shape up. If I were to have mapped those means from these many, many samples, and I took a whole lot of samples, these means would eventually map out to that normal curve. A little bit of a mind-blowing concept, but the key thing to think is that what we found is that it only takes about 50 or so of a sample size to approximate this normal curve, regardless of the distribution of the data in the population that underlies it. So that's good news. Our rule of thumb for statistics is we want at least 50. If we're comparing groups, we usually want about 30 to 50 per group. So if I know that I'm going to be wanting to compare men and women in a population, I'm going to want a sample size of at least 30 of each. Total population, total sample rather of 60 is over my 50 rule of thumb. A lot of different ways to do the power analysis, but it all boils down to how many do I need to make the particular statistical test that I'm running accurate enough and reduce my error enough so that I can get statistical significance and, in other words, infer a relationship where one is really there. If I don't have a large enough sample size, I'll just tend to miss stuff that might be there. I'll just point this out before we close. Notice we seem to have a sort of a bimodal distribution here. Got a little clump here, got a little clump here. So this is one of those opportunities where now I might go back in and compare against other variables. These are the school means. It may be that this is really perhaps a set of schools with very high poverty population, and this is our other schools. And then one group is really two groups kind of embedded within each other. I wouldn't know that until I do those correlational examples like we did in Unit 4, but it's a good example of where we can get some ideas from our recursive pattern. This gives an example of how that sampling distribution In other words, I've taken many, many means. I take a small sample of this. This is the population, how it distributes. Very odd, not normal at all. As I take all of those means, they start to stack up and become normal. The Khan Academy flip, I